In this lecture, I want to discuss the basics of gear trains. We'll continue on in Chapter 10. In the previous two lectures on gears, we talked about individual gears. And individual gears and understanding the mechanics behind individual gears and the design considerations behind an individual gear is important, but individual gears are ultimately used in gear trains. So gears have teeth, as I've previously mentioned, because we don't want to rely just on friction in order to transmit power between rotating shafts. The teeth allow us to transmit more power without having to rely on the coefficient of friction and the preload from the shafts. That's why we have teeth. Certainly the kinematics of a gear are the same or similar to the kinematics of two cylinders rolling on each other without slipping. Gears are efficient. Certainly spur gears are the most efficient with about 98 to 99% efficiency. So what does this mean from an efficiency standpoint? It means the following thing. If we look at this diagram here, we've got a electric motor, and that electric motor is rated at a particular horsepower, in this case watts. And that electric motor is transferring power from this pinion to a mating gear, which is going to rotate on this shaft, and that then gear is transmitting power to this other gear on this shaft. So the primary purpose of gears is to transmit power. Power actually is computed based on the following equation. Power is equal to torque times omega. In this case, we're talking about power in watts. So torque is in Newton meters and omega is in radians per second. On this slide, omega is denoted as small w. Efficiency, from a gear standpoint, is the relationship of power in times an efficiency is equal power out. So if we've got a 1 watt motor and our gear train is 98% efficient, then the output power is 0.98 watts. And the efficiency is based on or related to the amount of losses within each of the gears. And so you can imagine that as we increase the number of gears associated with a spur gear train, our efficiency would go down. Efficiency is also related to the types of gears chosen, the materials that you use, the lubrication that you put on them, and the conditions that they're in. So keep in mind, again, that gears and gear trains are designed to transmit power. We'll talk a little bit about the terminology within a set of gears. So the pinion is typically the smaller gear or the smallest gear within a gear train. A gear is the larger gear within a gear train. And gears are useful when they're found in sets. They'll be found in a minimum of 2, but you can have many different gears within a gear train. The driver gear is the gear that is attached to the input shaft and subsequently the power source. And the driven gear is the gear that is attached to the output shaft. Idler gears, and we don't see any idler gears in this figure in the upper right hand side of the screen. Idler gears are gears added to the middle of the driver and the driven gear, and they are used to change the center distance and the direction of the output. if you look on page 273, and this image is taken from that page in the book, we've talked about it before. When we look at the pitch line velocity, this pitch line velocity occurs at the pitch circle. So if you look at this figure, we've got teeth that are meshing, and it goes over the pitch circle, and it's less than the pitch circle. But this pitch line velocity is really where the power is transferred. So the point of contact of these teeth are along the pitch line. Pitch line velocity is measured in inches per minute, whereas rotational velocity is measured in radians per minute or revolutions per minute. Velocity ratio is how we define gears and gear trains, and I will go through the derivation of velocity ratio, ultimately leading to the fundamental law of gears. So if we look at a circle and we take a point along the circumference of that circle, and we connect the center point around which that circle rotates to this point A, the velocity of that point A is going to be tangential to the line connecting OA. We know that omega is at some magnitude, so we can determine the linear velocity of this point A, and we can understand the direction as well as the magnitude. This velocity is a vector. So that's for a single cylinder. If we look at the velocity of two cylinders, and they're currently not meshed and they're currently not touching, but if we look at the velocity at point A, we know how to compute the magnitude of the velocity of point A, and quickly speaking, the velocity of point A is equal to omega of A times R A. And we also know that velocity of B is equal to omega of B times RB. And these, in this case, for these two circles, are the magnitudes. They're just simply the magnitudes, and we can infer the direction. So this would be for cylinder A, and this would be for cylinder B. It's important to note that the values of the radii here are the pitch circle radii. Now when we bring these two cylinders together and we assume a no-slip condition, which is something good to assume when we look at teeth meshing, then VA is equal VB. In other words, the pitch line velocity at that point A and B is the same. When we manipulate the equation like we did last time, what we can compute from that manipulated equation is the following. Omega 2 divided by omega 1, so these are the rotational velocities of cylinder 1 and 2, is equal to plus or minus R A divided by R B. So I made a slight mistake here. We'll use the same terminology, omega B and omega A. So the plus or minus is there because the omega of A is opposite to the omega of B. So this is the relationship between the omegas of each of the circles based on the pitch line radii of each circle. So this is the fundamental law of gearing right here. This expression is the fundamental law of gearing. see if I can get this. Now we can apply a similar thing if we're looking at the transmitted force between two gears. So if we've got a cylinder A and a cylinder B, we can compute the force or the torque transmitted by each cylinder, and it looks something like the following. The torque of cylinder A is equal to the force at A times R of A. And in a similar fashion, the torque of B is equal to the force of B times RB. So, if we can manipulate these two cylinders and put them together, then here's what we know. That the transmitted force when meshed is equal. So in other words, FA is equal to FB. So if we bring back these two expressions into the fact that we know that FA is equal to FB, then we get the following solutions. We get FA is equal to TA divided by RA, and FB is equal to TB divided by RB. Manipulate those together, we get TA divided by RA is equal to TB divided by RB. And that ultimately results in TA divided by TB is equal to RA divided by RB. So the torque of cylinder A divided by the torque of cylinder B is proportional to the ratio of radius A to radius B. So we've got the following two expressions. We've got omega A divided by omega B is equal to plus or minus RB divided by RA. And similarly, we have torque A divided by torque B is equal to plus or minus RA divided by RB. This is known as the velocity ratio of the gear train, and this is known as the torque ratio of the gear train. If you look at these two expressions, the thing that you'll realize is the velocity ratio is the inverse of the torque ratio. Okay, so what does this look like if you were to go out and attempt to purchase a gear train or a speed reducer, or make a gear train or speed reducer? When you go look for a gear train or a speed reducer, usually what you'll find, and this is a catalog snapshot of McMaster-Carr, you'll typically talk about a gear train ratio. So this is a gear train ratio. It's related to the velocity ratio and the torque ratio. So a gear train ratio is typically expressed as a torque ratio, so 400 to 1. In this case, if you look at these catalog descriptions here. You can see that there's a 5 to 1, a 10 to 1, a 21, a 30 to 1, and a 40 to 1 gear ratio. These are called speed reducers, which means that the input speed is going to be reduced by 5 times, or the input speed is going to be reduced by 10 times. So that's how you would go and purchase a speed reducer.